All right, let's check the audio. Beautiful. And then let me bring up the thing so I can move this camera. Oh, wrong one. Yeah, that looks pretty darn focused. Sweet. Oh, wait, hold on. Am I on the wrong side? Or am I on the right? I'm on the right, wrong side. This thing is so backwards oriented. It's weird. Okay. All right. So summer 2, 5 weeks, differential equations. We are here. My name is Justin Hill. I'll be your teacher, your professor for these 5 weeks. And really, let's just kind of jump into it. So you guys can already see. You guys got my intro message. You can already see. So if you're through you should be through the orientation module. So you can already see that we have 4 sections this week, kind of 4 homeworks. Really quick, I wanted to mention, I know I mentioned it on the welcome email, but those homeworks, I just wanted to make sure you kind of understood how that was working. So literally, so today we're doing section 2.2, right? So actually what you want to do right now, I mean, if you need to pause the video for a second, is you want to go back to the orientation module where what do you call it? The little pages that gives you the ebook, the load button for the ebook. So go ahead and click in on that and open up the ebook. So I'm going to teach you section 2.2 today. You'll see kind of what I do is, honestly, I teach concepts, I teach ideas, I teach definitions, and then we use those to go through go through problems. So what you're going to see today is, like I said again, I really major on concepts and ideas because concepts and ideas that you guys have seen up to this point, and not just math, but STEM in general, concepts and ideas are your tools. They're what's going to get you everywhere. No problem is going to look exactly like the problem you've seen before, but every problem is going to use some tool that you use, at least in these classes. So you go into some theoretical, some research stuff later on in your job or career, then you're going to see some brand spanking new stuff. But even that, what we do is we try to use old tools and crack it, or we try to make new tools out of old tools so we can crack sort of new problems. So 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 um, so I'm gonna teach that way, but I'm gonna, so like I said, I'm gonna teach concepts, but the fodder I'm gonna use is the problems out of the book. So you need to have the ebook up, so that you can kind of look at the problems we're doing. What do you call it? Yeah, so you can look at the problems we're doing, and then when you get to the homework, sorry, this was a very long end around for homework. But when you get to the homework, the exercise sections at the end of each, the exercises at the end of each section, that's where you're going to be finding your homework. So unlike maybe some of your other classes before this, this homework is not built as some sort of, preset homework out of Cengage or uh, Pearson or McGraw-Hill or whatever. So you'll see, so you'll see what you should be seeing on the week 1 module now is there's a homework for 2.2, 2.3, 2.4, and 2.5. When you click on that, it's just going to tell you what exercises you're doing. But those homework pages are actually just upload pages. So when you get done with these videos and you get to doing the homework, this is really what I want to clarify. You are going to take out a piece of paper. Some students ask me if they can use a pad to write this stuff down, but so let me say this first. So you're going to take out a piece of paper. You're going to open up the ebook. You're going to go find those exercises that I kind of told you to work on, and you're just going to work them through. And then you're going to take a picture, scan that work, and then upload it straight onto that same page that has the exercises that you're working on. So in each week's module, you're always going to have a homework page for each section with what exercises you're working on there. And some students in previous semesters have asked me if you have an iPad or you have some sort of app or tech that allows you to write and all that kind of stuff. you can do that instead of paper. Just make sure that you can upload it as a PDF, a JPEG, or a PNG. It won't take any of the other file types. So whether your tech outputs it as that file type, or you can use something like Cam Scanner to like just convert it. Either way, just know on those upload pages for the homework, on the homework pages, it has to be uploaded either as a JPEG. What did I say? JPEG, PNG, or the other one. But the other one they use very often. But yes, so that's how you're going to be doing the homework in this class. Those pages. So you're really just using. Honestly, you're really just using Cengage in this class for the ebook, and on those home. But the homework's really done kind of through those homework pages. So it'll tell you the problem, the exercise you're going to work on, and you're going to do all your uploading of your work there. All right. So I wanted to clarify that before we started. But otherwise, let's just go ahead and jump into 2.2 and just start off on kind of the ideas and concepts we need in general. So you are taking a differential equations class. And if you remember from Cal 1 and Cal 2, you've likely seen a differential equation before. There's usually a couple sections or a couple places there where they sort of pop up the idea and say, hey, this is a differential equation. But then kind of like the whack-a-mole game, it goes down just as soon as it pops up. So you've seen it a couple times before, but they never really made a big deal of it. So let's make a big deal of it. So we are studying differential equations in this class. Well, the first thing is it's an equation, right? What makes it differential? So you study a ton of different equations, literally a ton of different equations all throughout your math classes. So what do you think they mean by differential? And even though I know I can't hear you guys answering or anything like that, it still just does help. Better lectures, or at least even if I can't hear you guys, I'm going to give you guys time to sort of respond to the screen, because when I ask a question and you process that and you figure out something about it, you say something to it. That's going to get you not only engaged, but really understanding what's going on in the lecture much more than just hearing somebody talk. So I'm going to do that on these lectures, even though the thing that sucks is you guys aren't here. I mean, if this was remote, it would be perfect because I could actually have you guys answering the questions. But even though you guys aren't really here, I'm still going to pause like you are. So I encourage you guys to just go ahead and answer the screen. Go ahead and shout into the void. But yeah, my son's back here screaming at the void. I understand. The void does need to be screamed at. But yeah, so I encourage you guys actually respond back to my questions. Just always remember, I'm sure you guys know, you guys are differential equations, you guys take a ton of classes, so I know you know this. Just always remember, it's not always about getting the right answer. So I ask a question, you respond back, I answer back something different. You actually learn a lot from your thought or the way you were going to go, something not being the correct way, right? Because there's actually more to be learned in why isn't this the correct thought or method than there is in sort of that self-validation of, okay, I picked the right answer and here's the right answer, right? You still get to understand why it's the right answer. You actually learn a lot more from picking the wrong path and figuring out why that's the wrong path and why this is the right path, right? So don't be afraid to answer the wrong answer. So I say all that to say, don't be afraid to answer the wrong answer. Just shout stuff at the screen as I ask questions. So I think my question was, we call these differential equations. So what does it mean by differential? Good. And maybe hopefully that triggers, I mean, just verbally, just verbiage wise, hopefully that triggers your Cal 1 and Cal 2 classes. Differential is just, just a what do you call it? Just another variation of the word derivative, right? So a differential equation is an equation with derivatives in it. Now, I'm not saying that that means we're going to take derivatives, so this is not Cal 1. Like occasionally you can take a derivative, that's fine, but so I'm not saying this is not Cal 1. What I'm saying is we are going to look at equations with derivatives embedded in them, built into them. So for instance, maybe we see something like this. Maybe y prime. So a simple thing would be like y prime equals sine of x, right? So this is an equation that's saying the derivative of y is sine of x. That's a differential equation. And maybe we have something like, you could have another differential equation, maybe something like y prime plus 3y equals 5e to the x, something like that. So again, an equation with a derivative embedded in it, but we also have the function y itself. And I can write some other examples, and I probably will, but really quick before we go on to other examples. So I'm saying this is a differential equation. It is an equation with a derivative in it. I think the second thing to think about is, what is the purpose? Like, so what's the end goal in a differential equation? So when we solve, when we solve an equation in algebra, or we solve an equation in pre-cal, we're trying to figure out a value for x, right? Or y, or whatever the variable is, but we're trying to figure out a value for x. So what are we trying to find here? What are we trying to solve? And maybe you have an answer to that, and maybe you don't. So I think for me, when I first took a differential equations class, I was looking at differential equations class. This was the first thing that was funky and odd about differential equations, right? Because usually when we solve equations, in some sense, let's just look at a very classic quadratic equation, right? Something like this. So 3x squared plus 5x minus 6 equals 0, something like this, right? Um, so when I look at an equation like this, so the goal of an equation like this, if they say solve this thing, then the goal is to go find x, right? So you have this variable in here that's present, and we need to figure out what that unknown value is. When I imagine an equation like this, so I'm a very visual person, so even with mathematics, I imagine things as sort of diagrams or movements, or kind of like shapes, which may or may not make sense to you. So when I imagine an equation like this, what I see is that you're starting with a small thing, kind of building it up, right? So I have an x and I square it. Well, that, naturally makes it larger, quote unquote, unless it's between 0 and 1. But nonetheless, I'm starting with sort of a small part. I'm squaring it, multiplying by 3, and I'm taking that same small part and multiplying by 5, and adding and subtracting 6. So I'm kind of taking these small parts, adding them together, getting a result. And my job as a solver is to go back and find sort of what that small part is, or what that initial part is, right? And most of the equations, not all, but most of the equations that you've faced in mathematics so far have essentially been like this, where you start with the nugget, with the piece, and things are done to it, and you're just trying to work your way back to find what that piece is. So the interesting thing to me about a differential equation is that, so we see these y primes, all that kind of stuff present in the equation. So even on something like this, your goal is not to find y prime. Now, like an equation like this is kind of silly because it tells you what y prime is, but we'll see plenty. So for instance, let's see, we could have something like, not let me get too crazy with this, but maybe 5y double prime minus 7y prime plus 3y equals, oh yeah, and there's a bunch of vocab that we should talk about as we're doing this. equals, I don't know, let's see if we did that. Let's do something like 5x plus 6. So we could have not only just not, just the y prime by itself, but you could have a y there, we could have a y double prime, you could have a third derivative, fourth derivative, you actually can have as many so as many derivatives as you want. So to give you guys actually some vocab really quick, I'll probably tell you guys this a lot, that I actually kind of hate vocab in mathematics because I feel like it separates you. You get so worried about having the right word that you forget that the ideas and the patterns are mathematics, whatever we call that term, right? Um, the ideas and patterns tell you what's true. You actually don't need to worry about a bunch of terms. However, as we not only for this homework, but as you kind of go through this class, we're basically going to look at classifications or styles and types of differential equations. And so in order to talk about them well and not just have the codifier for everything be this and that, it does help to have, what do you call it? It helps to have the vocab basically. And I think it comes up a little bit in y'all's homework as well. They'll ask you to identify a differential equations, this type or that type or whatever. So, so a couple bits of vocab before I go back into my point. So there's something, when we talk about differential equations, we talk about first order equations, second order equations, third order equations, and order is just essentially they're just using that for derivative. So the idea is, what is the highest derivative that you see in that equation? So these two would be first order equations. That's the highest C is the first derivative. This would be a second order equation. And then be a second actually to the other bit of vocab that I need to give you. I'm checking on this other vocab because in a differential equations class, this particular word has a certain meaning, and in other classes it has a slightly different meaning. So I'm actually checking the definition here, so I can give you guys the right definition for this class. Okay, well, there'll be a little bit of which we'll talk a little bit about now, but we'll kind of keep playing out. We'll play out in the next section, the next video, but also especially the next chapter. So like I said, so what we have so far is this is the first order equation, that's the first order equation, that's the second order equation. The other classification that we use for differential equations, and these are classifications, these are not like an either or thing, it's just you can classify the order, and you can also classify whether it's linear or nonlinear. And I want to talk about that for a second because That's part of why I was looking that up for a second. One, this book I actually don't like their definition for linear and nonlinear, so I was looking up the more theoretical kind of like groundwork definition, and so that I could maybe give us get you guys to connect with it a little better. So essentially, linear and nonlinear is not about, if you think about a linear equation, right? A linear equation kind of looks like something like this, but this in terms of differential equations is also linear. So linear and nonlinear are not what you would think from like an algebra class, right? So linear means, y equals mx plus b, right? In an algebra class. But in differential equations, when we say linear and nonlinear, what we're thinking about is on each of these, either y or its derivative or its second derivative, um, um, we're looking at what these coefficients are. And basically, as long as these coefficients are linear functions, then it is a linear differential equation. And if the functions are not linear, or the coefficients essentially are not linear, then it's not a linear, it's a non-linear differential equation. And that's really, that's how you decipher those. So these, in fact, are all linear because the coefficients are constants. Constants are, constants behave according, just constants are linear. So we'll decipher that a little more as we go throughout the class. But that's, in general, that's a way to, you're going to see this in your homework, then classifying it one way or another using that vocab. So that's what they mean there. All right, sorry. So let's go back to, let's see, we were talking about, so I was talking about a lot of equations that we've looked at so far, the way I've kind of visualized them and the way you might be used, just, the way that would help you think about them is that we're taking small parts are being combined together, and you're going back and trying to find that small part. And pretty much every equation you've solved so far, your variable in the equation is the thing you're trying to find. The interesting thing about a differential equation is, again, especially if you look at this first one, if I was going to solve this, I am not trying to find y prime. I'm trying to find y. And in like this differential equation, even though there's a y prime and a y double prime, I'm not trying to find either of those. I'm just trying to find what y is. And when you're reading these differential equations, the way you want to really read this y, I think the other difference that you're going to see this whole 5 weeks, and really the whole where we've gotten to in mathematics. So in college algebra, pre-cal, you were worried about a number. A variable was a number, it was a value. And then hopefully you saw in Cal 1 and Cal 2 that, when we take the derivative of something, we don't find a number, we find a function, right? And when we take the integral, we find a function. So in calculus, we started carrying we definitely found some numbers when we needed them. We needed a slope, when we needed an area, etc., limit. But overall, we were actually more concerned with finding a function as an answer. When we took a derivative, when we did an integral, the answer was a function. It was defined over, a domain of x values, but the answer was a function. It wasn't a number. So if that didn't sort of hit you when you're doing your calc classes, I do want that. I want to throw that out there for a second and let that absorb into our amoeba brain. That you're really doing something like next level, more interesting, but it's just next level in calculus than you were doing before that, because your answers, you were trying to find functions. So when you're solving differential equations, you are not sure. Y is not a number, y is a function. So the way that I kind of visualize differential equations, whatever differential equation you ever look at, no matter how funky these parts start looking, what's happening with differential equations is there is some base function. And that function, the work you're doing to it now, we are still doing some multiplication and addition, but the main work you're doing to it is taking derivatives. So you have an equation that has the presence of derivatives. What I know is the derivatives of some unknown function. So I know the second derivative, I know the first derivative, etc. And I want to go back and I know the result of all of those things. So I know 5 times the second derivative of y minus 7 times the first derivative of y plus 3 times y equals 5x plus 6. And I want to go back and find what does y have to be so that all of that gives me 5x plus 6. And so I would say that these equations, at least in my mind, they're sort of backwards from what we normally do with all our equations before this. And all our equations before this, we took some, some, what do you call it, some piece, some, what's the word I'm looking for? Some ingredient, some little nugget, some ingredient. You build stuff up out of it, and you're going to go back and find that ingredient. When I take a derivative, I'm finding a function, in some sense, I'm going down the ladder. So the way that I think of differential equations is we're actually our ingredients are sort of, I don't know if I know what I'm trying to say, or like, if I know how to say what I'm trying to say. Well, just basically that these equations are made up not of some piece that you're building up, it's kind of some piece that you're breaking down, right? So you're breaking it down to a first derivative, you're breaking it down to a second derivative or a third derivative or whatever. You're putting those together, and your goal is to go back and, again, not find the first derivative or second derivative. You want to go back and find the original piece that you broke down. So at least to me, in my mind, conceptually, that's a lot different thing. So, your variable is not the same all the way across, but we actually don't care about y prime and y double prime in a differential equation. So let me try to summarize without my weird, what do you call it, a meta philosophical thing. What you're trying to do always in a differential equation is you don't actually care about what the derivatives are if you're trying to go back and find what the original function was. So your goal is, what is the original function that when I do all these derivatives and combinations to, I get, in this case, what's on the right side of the equation. So I don't know, that was probably unnecessary, but maybe not. But that gives you an idea of kind of when we solve these differential equations, this whole class, no matter what they look like, no matter what differential equation you could ever write, for not just for a class, so if there's some problem you're working on, some work you're doing in the future. Goal of the differential equation is to find the original function y. That's what we're going to be trying to do. Today we're going to talk about one type of differential equation that arises from basically first order equations. So actually this whole first chapter, we're going to talk about first order equations. And let's see. Look at it. I did choose some problems from the exercises. So again, if you want to go ahead and bring up, if you haven't already, if you want to go ahead and bring up, if you want to go ahead and bring up the textbook, go to section 2.2, and then let's see. Oh, it's basically the same thing. Yeah. We're going to look at an equation very much like this. So again, in this first chapter, we're going to look at first order equations. And I want to start by looking at equations that look very much like this. So I think we'll just go ahead and try to solve this equation. So we have first order linear equation. First order equation, y prime equals sine of x. and we want to solve it. So again, our goal is to figure out what is y. So I want you guys to remember too, it's not that we have to write this two different ways or anything like that, but I want you to remember from your Cal 1 and Cal 2 classes that you could also write y prime as dy dx. So I want you to want to just highlight that this book does a pretty good job of kind of splitting the middle. Like you'll see some problems written in the prime notation, you'll see some written in the dy dx notation. Basically, Newton's notation and Leibniz notation. Means the same thing though. You will find sometimes we'll come talk as we go through. Sometimes this notation helps us with some of our solution methods, and sometimes this notation is better. Kind of the same that you saw in Cal 1 and Cal 2. Sometimes they would switch to this notation, Leibniz notation, because it actually helped them with their what do you call their solving procedure. So for instance, stuff like chain rule and stuff like that, for integration by parts, are just conceptually you can't really do all this. You can't do it this way, etc. So we'll see that in a little bit in this question. But let's make this first equation. We'll solve this thing. So give me your thoughts from what you know. Cal 1 and Cal 2. Stare at this for a second, shout at the screen. How do you think you'd solve this? So maybe hopefully you look at this and you realize, well, it's telling me the derivative. So the nice thing about this equation is there's no other derivatives present, and there isn't even a y present. It's just y prime. So this is telling me the derivative of y is sine x. So if I know the derivative of y is sine x, how could I figure out what y was before I took the derivative? Good. So the key here is remember from Cal 2 that the integral is the antiderivative. It's the opposite of a derivative. And in some sense, the way you can think about this is it's kind of like when you're solving algebraic equations, you got y by itself. You have y prime by itself. So all you got to do is take an integral of this. So take an integral y prime, which means I'm going to integrate this side. And then that'll give me my answer. Because when I integrate y prime, I get y. And when you integrate sine of x, what do you get? Give you guys any those. So now that you're done with Cal 1 and Cal 2, let's use it immediately. What is the integral of sine x? That's going to be negative cosine x. And then you want to add a c to that. So there's some unknown constant that could be there. And you've got it. That's your value for y. So I bring up this problem because the first thing you want to think about when you're thinking about differential equations is, and most of the time we won't be so lucky, but still the groundwork that we're going to work up from is I would like to have a derivative by itself. I would like to be able to kind of, kind of clear everything so that I have the derivative by itself. Because if I can do that, then I just integrate and I got my answer. By the way, writing this in Leibniz notation. So this is good. This is correct. We don't need anything else. But just so for some of the work that we're going to do going ahead, if you have this in Leibniz notation, the way that we sort of officially do this, treat this notation is usually what you do is you multiply by dx on both sides. So you basically move the dx to the other side. Again, hopefully this is just this is just ringing bells in your memory as we do this. And then I'll integrate. And then an integral of dy is y. And then an integral of sine dx is negative cosine x. Let's see if this first time. And you get the same answer. So there's nothing inherently better about this way of writing it versus this way of writing it. Get the same answer, it does the same thing for you. There's just basically slight, again, like I said, slight differences in algebraic procedures that you can work forward, depending on whether you do the dy dx or the y prime notation. So, but again, so the groundwork we're going to work from is we would like to be able to get a derivative by itself or isolated. That's the word I was kind of reaching for in my mind. Isolated in some way, so that we can take an integral into our work. Right. So serves those. Actually, let me have you guys. So I'm going to put a problem up here. And I'll kind of explain how we'll go through it, but let me put a problem up here. So let's look at something like dy dx equals x plus 1 squared. And so what I'm going to have you guys do is I'm going to have you work this problem. So the way we'll work this, since again, you're not really there, I'm just speaking to a video, is I'm going to have you guys, so you'll pause on your side, I'll pause on my side, and just go work this problem. So take a minute and work this problem, and then unpause the video. Through the magic of technology, I will also be unpaused, and we'll go through the problem from there. So you can kind of compare and contrast what you did versus what I'm doing. Just make sure you're getting to the same place, getting the same answer, understanding why what you did worked right, and what you did was right, or if you did do something wrong, why it was wrong, and why the correct thing is the correct thing, right? But that's what we'll do. So I'm gonna have you guys work on this problem. You pause on your side, I'll pause on my side, and then we'll come back to it. Easy enough. Again, the point of this is, again, just for you to see, if we've got an equation where the derivative is isolated, then we just take a derivative and go, right? So rewrite this as integral of dy, we'll do the integral of x plus 1 squared dx. And so what you should have got here is the integral of what it's going to be x plus 1 cubed over 3. Sorry, not integral. Is going to be x plus 1 cubed over 3 plus c. That would be your answer. Now, this is all there is, then this wouldn't even be a class. I mean, I literally would have just shown you this problem on sidewalk chalk or something. You know, like it's like if this was all there is, then there wouldn't even be a reason to be here. So obviously, and unfortunately, most of the equations, a lot of the equations we're going to look at are not so nice. They're not just a derivative by itself. Kind of makes sense. This is the base. This is the simple. We're going to start adding pieces on. But for today, today, like I said, we're talking about separable equations. Separable equations are equations that we still algebraically we can separate them so that you do have a derivative, or at least something you can take an integral of on each side of the equation, basically. So that's what you're looking for, is can you separate the equation out algebraically into essentially what you're doing is y is on one side and x is on the other. And if you can do that, then you'll be able to integrate both sides and basically play this game. So that's what we're looking at today. Separable equations, things that we can, after we do some algebraic manipulation, we can, or it does end up looking like this, and we can take we can take a derivative. So for instance, let's see, do I want to skip this one? Kind of, I've already done it. Well, no, yeah. So if I see an equation like dx plus e to the 3x dy equals 0. And again, this is a differential equation. It has a derivative, kind of rearranged algebraically in pieces, but we have a derivative there. So a derivative of x to a derivative of y. And we wanna solve this differential equation. Let me make sure to make sure the video is. We're not. Make sure I'm not on the edge of the board. We're good. Well, like I said, they're calling the equations we're going to look at today. They're calling them in general separable equations because the idea is I should be able to look into algebraically be able to separate things off onto each side so that I can't take a derivative. So, for instance. One thing we could do here is we could, and you don't have to write all this down. I'm sort of writing this down just to be complete for the first couple times through, or first time through. But I'll subtract e to 3x dy. At least we have dx equals negative e to 3x dy. And then if you divide by dy, notice that voila. Voila, you have a derivative. Well, sorry, where do I want it? We have a derivative of x though, so it's actually upside down. A second. Okay, so what I'm saying here is I would like solving for y, so I would like this to be dy dx instead of dx dy. So instead of that, I want dy dx. So let's go the opposite. Let's divide by dx there. End up with 1 equals negative, not kind of 1 equals negative e to 3x dy dx. Then I'd like to be able to isolate this, so isolate my derivative. So I guess I could have done that initially. There's something wrong with. Oh. So we're going to move this over to this side, but to move it, we've got to divide by negative e to the 3x. Divide by negative e to the 3x. And then just remember from algebra that if I'm dividing by a power, that really, well, one way we could rewrite that is it's a negative power. So I can rewrite this as negative e to the negative 3x equals dy dx, and then integrate and go to town. To make it look right, let's move the dx to the right. Multiplying by the dx there, and then we'll integrate both sides. Sorry. So there was kind of an unnecessary step, but nonetheless. But this is what we're looking for, is we're looking to separate it so that we can integrate things on both sides. So let me, again, this will be a short one for you, but let me lead you to this. So pause on your side, I'll pause on my side. Go ahead and solve this real quick. All right. And we're back. I do want you to notice something about this. So again, I kind of keep telling you, we're trying to get the derivative by itself. But notice by the time we do this integral here, we kind of need the x's with the x's and the y's with the y's. There's not another y here. But you'll see that in some kind of, I won't try to foreshadow too much, some problems coming down the line, that that makes these integrals read in the form that we're used to. Whenever we take an integral, we need a dx with our x's and a dy with our y's, right? All right. But taking the integral here, let's see what we get. So what did you guys get for the integral on the left side there? Good. So the integral there you should have ended up with what? So we're basically gonna sort of move this up to, it's gonna be an e to the negative 3x, but we're gonna divide by negative 3. So this is gonna be e to the 3x, sorry, negative 3x over 3, and a plus c. And then when you integrate the right side, that's gonna be y plus c, right? Or plus, so we'll call that C1 and C2. They're two different constants. And then we just need to get y by itself. So the point to make here that, again, hopefully you guys remember from Cal 1 and Cal 2, I'm basically just moving the constant on this side. But when I move the constant on this side, again, these c's are just representing some, some constant, some value you don't know. So I can just move it on this side and call it c. So what we end up with is y equals e to the negative 3x over 3 plus c. And that is the solution to our differential equation. So let's keep going with this. Let's look at some more problems, especially where we're just adding more pieces in here with some more mixes of x's and y's. So I think the next one I wanted to look at. Let's look at something like, so this is 5, but so these are all the exercise numbers in the book. So x dy. This one is x dy over dx equals 4y. And I want to solve that. Oh, that's what I was trying to do. Let me move this camera. Let me see what the view looks like. Yeah, so you guys can't see that right now. So let's do this. Okay, that'll work fine. X dy dx equals 4y. So again, what we're going to want to do is we want to, like I said, we want to isolate our derivative. So I want to take this one direction here, and we'll kind of look at why we're going to start to. We want to say we isolate our derivative. So we're going to start to do something slightly different to kind of help us do that. So the derivative is here, dy dx. So if I isolated that, I would have dy dx equals 4y over x. So the one thing I want you to think about now is, if I then try to take the derivative or the integral of this, can I take the integral of this right side? Good. I can't take the integral of this right side because I need this to be in one variable instead of two, right? So again, notice on this last problem, when I was moving things around in the end, I did have the dy dx. But I have, and I actually didn't have to here, but I kind of moved the dx over here, and I was talking about how this is just the form we're used to seeing when we take an integral. We always have a dx on the end of an x and dy on the end of a y. So here it wouldn't have mattered. I mean, really, if you just wanted to take the integral of negative e to the 3x, you would have got the same exact thing. But here it's going to matter. So, because the problem here is that this is fine. I can, this is y prime, and the integral of y prime is y. But I don't know what the integral of 4y over x is because I have mismatching variables there. So instead of stopping here, what I want to do is like we did on the last one. Basically, let's get the dy with the y's, and let's get the dx's with the x's. So essentially, what I'm going to do here is so a little rearranging. I'm going to I want the dx up here, so I could multiply by dx and I get it up here, and I could divide by 4y and I would get it down here. So I'm going to change this. We're going to modify it, and it'll end up being dy over 4y, or kind of 1 over 4y dy equals dx over x. And then I can integrate. Because now I have the familiar form I kind of need for integrals. Again, I'll just rewrite this really quick. So this is 1 over 4y, or you can think of it as 1/4. Well, I'll keep it that way actually. So this is 1 over 4y dy. And this is 1 over x dx. So then you got to kind of ask yourself, what's the integrals here? So now we can't take the integrals. And what do you guys remember? So when you have 1 over a variable, what's the integral of that? That's going to be natural log. So this is going to end up as natural log of the absolute value of 4y plus a c equals natural log of x plus another c. Now again, my goal, so this is all correct work. Like I said, your instinct is you want to try to get the derivative by itself. And then if that doesn't work, what you want to do is separate out your y's and your x's. So again, this is why they call this a separable equation. So there are linear equations differential equations like this that you can separate out your dy and your y and dx and x. If you can do that, then you're always going to play this game. And then algebra will, your algebra work will kind of get you the rest of the way. So this is, let's say, honestly, these first two examples, they are separable equations, but we recognize that we can just take the derivative and go. Whereas these last, even the third example, but this is the first one where really, again, you can't just get the derivative by itself, but you can separate out your dy and your y, your dx, and your x. If you can do that, we call that a separable equation, and that's the strategy you're using. But again, let's think about overall solving a differential equation. So what's my overall goal? My overall goal is to get y by itself versus to solve for y, and you figure out what that function is. Good. So really quick, what I'm going to do here, so keep doing this so we can keep using this line. So I'm going to have natural log of 4y. I'm going to move the constant to the other side, natural log of x plus c. Then to get y by itself, remember that natural log is e to have a base e. So I'm going to rewrite this. I'm essentially going to talk about that now. I'm just going to rewrite this in exponential form. So in exponential form, This is e, the natural log of x plus c. That all equals so the one thing I always hated in calculus is it is correct to put those absolute values there, but then often algebraically when we're solving things, we at convenient times just lose them. And I think that's what we're gonna have to do here. But there's an example like this in this section. So let me see if basically if the book is fine with us just sort of conveniently losing it, then oh, I see what they're doing. But what about that part? Mm. Oh. Mm. Oh, I really don't like that, but that's okay. All right. So we get this equals the absolute value of 4y. And then what we're going to do here is take some properties of exponents we know. So notice here you have e raised to a power plus another power. We know that with powers, we add powers when we multiply with exponents. So we can rewrite this as e, the absolute value of natural log of x, absolute value, natural log of x. That'll be then times e to the c power. It's the absolute value of 4y. Now I have e raised to a natural log. E and natural log have the same basis, so they cancel, and what you end up with here. Yeah. I don't want to focus too much on some of the theory here, so there's a reason for the next kind of move I'm going to do, and I don't, because this is a 5-week class, I just don't want to get lost in a bunch of theory. So give me a second here. Well, so then that leaves me with the absolute value of natural log of x times e to the c equals yeah, equals absolute value of 4y. And then the theory here is remember that absolute value is essentially the idea is absolute value always comes out positive, right? So wherever sort of the center of this would be, it will come out either the natural log of x would have been either a positive number or a negative number, but it comes out positive always because of the absolute value. So to not dig into a bunch of theory, if you forgot these absolute values, you can replace them with just a plus or minus essentially. So we can replace this, and I'm gonna with 4y equals plus or minus. Sorry, this should be x, not so absolute value of x. Because this should have been, sorry guys, it should have been absolute value of x to begin with. That's what I was telling you. Yeah, so absolute value of x. So we can rewrite this as 4y equals plus or minus e to the c times x. And then we can divide by 4. And we finally have it One of the things they will do in both in the book, but they do pretty generally solving differential equations is, so we have this e to the c, right? But c is a constant, so this is e raised to a constant, but e is a constant. So this e to the c is some number. Again, I don't know exactly what the number is, but it's determined by whatever e and c are, so it's not like it's a variable. E is definitely a number, c is a set number. So basically what they end up doing is they end up rewriting that as just a c, a general c. So plus or minus cx over 4. And that's my answer. So this would be the solution to that differential equation. So like I said, this is where we really get into, again, those were separable equations, but this is, when they say separable equations, that's really what they're referencing. It's equations where just getting the dy dx by itself doesn't do it. You need to actually separate the dy with the y's and the dx's with the x's. And then you end up integrating both sides because it's in the form that you guys saw in Cal 2. That's the standard way we write it out that we can integrate it. Good. All right. So let's play with a couple more kind of very pure separable equations like that. Oh, sorry. Seven, so let's look at 7. dy dx. E. For the 3x plus 2y. And they're going to ask us to solve this. Now notice again, sorry, just start thinking this way through forward. So notice they do give us dy dx by itself, but kind of like 1 or 2, it seems like, okay, let me just take an integral and go, right? But what's the problem on the right side? If I try to take an integral of this, what problem do I run into? But it's not a function of one variable. It's a function of two variables. It's an x and a y. And I definitely, I mean, I don't have the dx or dy over here. But even just from a theoretical patterns, just a definition standpoint, I can't do that. I can't integrate something with two variables like that. So kind of like this last one though, we're betting on there's a way to rearrange this where we can get the sort of x's with the dx's and the y's with the dy's. And notice that you have an e raised to, again, 2 powers being added together. So that same algebra trick from the last problem should probably be important for this problem, or should probably be at play in this problem. So how can we rewrite this right side? So using properties of exponents, how can we rewrite this right side so that it's not just e to an x power plus a y power? Good, this plus, I can rewrite that as e to the 3x now times e to the 2y. We don't really need to write the times. Good. And now notice you have two functions. You can have two pieces multiply here. And algebraically, I should be able to manipulate this to get the y's with the dy's and the x's with the dx's. Good. So that's what I want to leave you to do. So you've seen this kind of a couple times in the last two problems, like just in general, kind of separate your the x's with the dx's and the y's with the dy's. So see if you can play that out this time with all the output that you know. And then see if you can get the answer from there. See if you can integrate it with the answer. So you pause on your side, I'll pause on my side. See what y'all are trying to. Okay, so again, honestly, one way to think about this is multiply by the dx, divide by the e to the 2y. So you end up with what do you call it? So when you divide by the e to the 2y on this side, that's gonna be on the bottom fraction, so that's actually negative. So it'll be e the negative 2y dy equals e to the 3x dx. And then we need to integrate both sides. So integrating the left side, you're going to end up with is it basically negative e to the negative 2y over 2 plus c. So at some point here, what I'm going to do is I'm just going to put 1 plus c in the problem. We know that it's two different constants, but you're going to end up subtracting them and getting one gigantor constant anyways. Good. And then this one is going to end up as e to 3x over 3. Good. So we'll move the c to that side. But more importantly, so now we're going to have e to the negative 2y, and we got to figure out a way to sort of get y by itself from there, basically. So let me rewrite a couple things here. I'm going to move the c. I'm also going to I'm essentially going to multiply by -2 just to get rid of all that in front. So what we're going to end up with is e the negative 2y equals negative 2/3 e to the 3x. Good. Then what we can do, kind of opposite the problem that we just did, is we can turn this into a natural log. So this is going to be negative 2y equals natural log. Although actually, hold on a minute. Okay, yeah. Natural log of negative 2/3 3x. This was all plus c basically. Okay. Oh, that's what's gonna kill this problem. That really sucks. Yeah, that's what's gonna kill this problem. Oh, okay. They did. Well, yeah, let's do that. So you can end up here and we can divide by -2. Yeah, 3x, sorry. So what I'd like to do, kind of similar to what we've been doing with exponents, is I'd like to break this apart somehow. And if this didn't have the plus c, we actually could. We could treat this as two kind of pieces being added there. Maybe, but let's do it in a second. Is that what they're doing in the end? Yeah, no, they aren't. Because it's this plus c, we're not going to be able to do that. So the best we can do is kind of divide off by the -2. So I'm going to end up with y equals a -1/2 natural log -2/3 e to the 3x plus c. And that is good enough. So that does give us an answer for y. That is our function y. All right, so as long as we can separate our y's with our dy's, our x with our dx's, then we can solve this. All right, let's looking at a couple other problems. I think what I want to do is I just want to do a couple more problems. Again, you'll just kind of notice it. Problem, the kicker is always where you're doing the integral. So honestly, this, not just this section, but this whole first chapter is a giant kind of remind yourself of all the integration technique that you learned in the last class. So I will say in general, this class is a giant, this is Mufasa and Lion King after he's died. Remember, who you are. Remember all of your integration that you did in Cal 2, because every bit of it is going to come into play. So that I want to throw that out there. So the problems you're going to see in the homework are going to involve a lot of the integrals we saw here, but some of them are going to be integrals we didn't see here. But you guys already passed Cal 2, so you already know those. But I know that was a lot. So just call all those to mind and just know that that's the challenge that you're looking for. That's kind of what you're going to be doing, not just on this homework, but all homeworks. And that's the challenge you're going to be looking for, is calling back all of the integration that you kind of learned over Cal 2. Good. No, so let's do. I think what I got to do in the future is I got to plan a couple miles. But let's go to. So the only other thing they kind of bring up in this section, that is, again, it's still we're solving separable differential equation. But they bring up what's called initial conditions. And so you see this a lot, honestly, in physics, chemistry, etc., when they're modeling physical systems. So when they model part of, again, the overarching thing, say the overarching narrative of differential equations. So I think a legitimate question kind of out of this and out of everything you're going to see in this course is, okay, well, why does this exist? Why do we even have equations with derivatives in it? Like, that doesn't even make any sense. Because a bit like I was trying to get to earlier, up until now in mathematics, we've been concerned about the function y. And we've taken a derivative, yes, that had some application, some nice purpose out of it. But our main focus has been the function and then we do something to it. And again, so this is what I was trying to say earlier, differential equations are in some sense the reverse. Our focus is the derivatives and we want to work our way back to the original function because we don't know the original function. So a fair and legitimate question is, why in the world do these equations exist? It's just some mathematician farting around, just being like, hey, I can write these, let me figure out how to do something with that. And for a mathematician, that's a legitimate enough case to sit around and do this work. But for anybody else, it's definitely not a legitimate case. So why is this around? So the interesting things that I would say actually differential equations came naturally not from a mathematician, but from physicists and chemists. Because when you model systems, you think about again, being an engineer, being a physicist, being a chemist, and maybe you're studying like electromagnetic fields, or you're studying some chemical process or some chemical pathway. So the interesting thing is, if you think about it, if you think about experiments you could run and just kind of trying to figure out things about reality. So maybe in civil engineering, you have something like this room, right, where everything's kind of static. You study the forces going on. But the interesting thing in physics and chemistry and engineering is that most things that happen, most systems that we're looking at are not static systems. They're actually moving systems. They're things that are happening. If you think about it, even just a lot of the basic ideas of physics itself, right? Velocity, acceleration, etc. To know the position of something, right, you have to freeze time, you have to freeze frame. The natural, so that's not actually natural to the way our universe is. The natural setting is the wrong word, but yeah, the natural state of the universe is movement. Things are always moving. And so if you think back to some of those ideas of the derivative and Cal 1, or if you've taken a Physics 1 course, you know that basically, I mean, the derivative, that was really the use. Newton and Leibniz invented the derivative to track motion, to track, not just things in motion, but properties and quantities of particles and whatever but it tracks the motion of these things we're interested in, whether it's energy, whether it's whether it's energy or whether it's electric field or etc. So the interesting thing when you actually get out there and try to model a lot of systems is that you don't often have the benefit of having some knowledge, some knowledge of the static amounts and positions of of a certain thing or a property that you're trying to study. What you usually have is their speed, their velocity, you have the change in kinetic energy over the chemical pathway that you're looking at. You have changes in things. Changes in things are derivatives. So when you're studying things in reality, it's actually much more common that the data that you have will tell you a model for the derivative, but not the original function, not the static function. It tells you the amounts when you freeze frame the universe, right? So it ends up that differential equations actually come up a crap load when you study science and when you study physics, chemistry, engineering. You can model the change in some property very easily. The harder thing is to model is the freeze frame and be able to model the original function, right? So it ends up that differential equations are hella useful. We often can only model the derivative or the second derivative. We can model velocity and acceleration. And from that, we can work our way backwards to the original function to find, position. So it is actually, I would say, more often that you have that the equations that we use to model situations are differential equations, and we need to learn how to figure out the original function from that. Anyways, so I think so that's actually the reality of being a scientist, being an engineer, is that you more often will know differential equations than you do static equations of properties. So what we're doing then is we know the differential equations, we know the change in the movements and properties and such, and we're trying to model the original function, the static function for the system. Notice that all the solutions we've been coming up with have this C at, they have the C at the end because that's what happens when we integrate, right? They have a constant that when you take the derivative goes to zero anyway, so it could have been there. When you're modeling these systems, the interesting thing is that these answers we're getting won't tell us the precise condition of the original system because of this plus C. So one way to think about it is, let's say we solve this differential equation, right? So let's say, sorry, you guys may not be able to see that. Barely, but let me move it over. Okay. So let's say we modeled a system and this was the differential equation for it and you went and solved it. So this is the model, this is the equation that should govern the original system that you're looking at. But notice that, so think about this in terms of college algebra, what this is a cubic function, but it's plus C, and our plus C changes our y-intercepts, or basically our vertical our vertical position, which means that your original system, the model for it could be centered at 0, or it could be centered at 1 or 2 or -1 or -2, etc. Could be centered anywhere up and down. So this solution is actually not even just one function, it's what they call a family of functions or a family of solutions. It's a family of cubics that, your real solution for your original system could be anywhere, could be this function, but it's anywhere up and down that graph. So then, as an engineer, as a scientist, the question is, well, how do I figure out which one of these family of solutions, which one of these original solutions it really is? Because again, with the math, with the integration, I can get this family of solutions, but I don't know what C is. And so the way you figure that out is usually with the system that you're studying. While you may not have any information about the original function, you may have the information on the condition of whatever property you're studying at one place, sort of one for one x value, at one place in your system. So you have what they call an initial condition. Basically for instance, when x is 5, then y, my function, equals blah. Or when x is -1, then y equals blah. So one pair of x and y of your original function for the system to begin with, and they call that an initial condition. And then if you think about it, not just surprisingly, that'll be enough to figure out your C. So if I know the x and y pair, I know one solution of this little general solution that I just got, this family of solution. And you plug in the x and the y and you go find the C, and you've got you've now pinned down the exact function that models your original system. So that's what we're going to do in the next couple problems. Is we're again going to solve these differential equations, but we're going to go one step farther. We're going to have an initial condition which will allow us to solve for C. So we now have not the general solution for that original system, but the exact solution for that original system. All right, let's do that. At least one more, maybe two. So. So I think let's start with. Maybe we just do one of these. I gotta just. Yeah, let's just do one. Or this. Well, you guys don't see what the process is. It's much easier for me to teach when there's actually students here, or like a remote class, because I can bounce off of what you guys are saying, where what you guys aren't understanding, what you guys are working with. But actually, usually when I teach face to face or remote, it's a 2 hour lecture at the most. But when I do these videos, the problem is I need to take time sort of between to basically plan what the next step is, because normally I would use my feedback from y'all. That's my next step. So I'm very good at that. As a teacher, I'm very good at theater. But planning a whole lecture out before anticipating all possibilities, that actually just takes a lot longer anyways. So what you guys don't see on your slide is this is taking a bit of time. So let's go through one example with initial conditions, and we'll keep doing initial conditions. Actually, I think I pretty much all these sections. So we'll come back on that next video for the next. So I think what we'll do is this is 25. X squared d by x minus equals y minus xy. Good. So that'll be our differential equation we're solve. And like I said, they're going to give us one extra bit of information. They're going to say that y of they're going to say y of -1 equals -1. So what equations once we solve for, we then are going to know that basically when you plug in an x of -1, you get y, or you get -1 for y. So we're going to use that information then to figure out our c. But first, we've got to rearrange this. So again, what you see here is hopefully something where you can separate this into your x's and dx's on one side and your y's and dy's on the other side, and then we can integrate both sides. So again, it's separable equation or linear differential equation. All right, so let's see if we can separate this. So I guess that's kind of the first question is, what do you guys think? So what you're also gonna have to get used to doing as you're doing these problems is, again, you're the problem solver. So you've got to be able to see this, so algorithmically playing this with this in your head and trying to move things around and see if it does work. So I think that's what we'll do first is I'm going to pause, go ahead and pause on your side, see if you can get this separate, basically. Y's and dy's on one side, x's and x's on the other side, and then we'll come back at it, go from there. All right, so let's see what you guys are getting here. So this one's fun because we definitely have some pieces. We have pieces with several different kind of combinations of x's and y's here. But what I want, let's see. I think what I'd first do here. I think what I do first here is I would factor out the y there. I have x squared dy dx equals y times 1 minus x. And I'd start sort of migrating the dx and the x squared over to this side. Yeah, dy equals y times 1 minus x over x squared dx. And then I divide off the y, so we end up with dy over y equals. And now what I'm going to do, just to help me with my integration, is this 1 over 1 minus x over x squared. I can break it apart into two separate fractions and work, kind of rewrite the pieces. So I'm going to end up with, I'm going to write it this way: x to the negative 2 power minus x to the negative 1 power all dx. And here now I have dy and y, I have x's and dx, so now I can integrate. Good. Now we have to integrate from that. Let me see again too. This book is also getting a bad habit of. No, okay, they did do things. They did some. So, um, so then the next thing is we want to then work the integrals so we get the general solution. And then, like I said, after that, we'll start plugging in to see if we can to figure out what that C is. So your next job is go ahead and get the general solution. So go ahead and pause on your side, I'll pause on my side, and let's work that through. Where are you all got? So we know the left side ends up as the natural log of y. And then on the right side, so this is x to the negative 2 power. Integrating, you're going to bump that up to power up to negative 1 and then divide by that negative 1. So you end up with negative 1 over x, or x to the negative 1. Now x to the negative 1, if you bump the power up 1, that's a 0. So again, remember 1 over x, when you integrate it, you get natural log. So this is going to be minus the natural log of x plus c, absolute natural log of absolute value of x. And then, like we've done on several of these now, I'm going to reform this. I'm going to get the y by itself by essentially rewriting it as a, what do you call it, exponential. So we're going to get y equals e. E to the negative 1 over x minus the natural log of x plus c. Let's keep that as f value. I see. That's what I knew that as. Let's see. That's what's we. All right. All right. So then, so again, so this is our general derivative. Our general is our general solution. Now what we can do is we can. So now again, we know something extra on this problem. We know this initial condition. So we're going to plug this in for sort of our x, our y. And then we're going to go see if we can solve for c from there. So let's see if we can do that. Yeah. That's nice. So this still should have the absolute value of y around it. I want to play the game like we did on the earlier problem where we sort of used plus or minus to get rid of those absolute values. Might not be able to do that. Let's see what. I guess. Well, just as a note in general too. Talking about this last. So in terms of mathematics, where we learn how to calculate and solve things, or kind of have these tools for engineering purposes and science purposes. Differential equations is definitely the highest level we're looking at. I just because of my schedule, I actually usually don't get time to sort of work these problems out beforehand. But also because I'm a person who likes puzzles and likes challenges, and has a PhD in math, I actually kind of don't want to work these out at a time because to me it's the true challenge is solve the puzzle when you see it, right? So I will say that you'll see as I'm doing these problems, sometimes I do have to pause because especially because this is the highest level of as far as calculational tool using math. I definitely will have to pause sometimes and kind of sort these things through my head. Because even I have a PhD, I have published papers and citations on my papers. But even I, for this level of math, I've got to look at it. And like I said, it's a puzzle. I've got to look at it and be like, hold on, it's not going to work how it's going to go, or this doesn't work. The algebra that I was thinking will get me to the end of this problem isn't going to work. So what's the other option, etc. So you'll basically kind of watch me a bit solve in real time these problems. So hopefully you learn a little from that, or maybe it encourages you that like that's the real kind of reality of math once you hit this level. Is you know, besides those crazy mathematicians that are solving 100-year-old problems, working at I don't know, whatever, Penn University or something like that. But you know what I'm saying. Like besides those people that are just their brain is just doing something, either their wiring is doing something at a level where that others can't. Um, the rest of us, like this is normal. The rest of us really need to look at it and work it through and solve it, right? So maybe I can visualize that better than you, and maybe not, and maybe I can work it faster in my head than you, and maybe not. So just sort of be encouraged that like that's you're doing well. That's the reality of this. So again, so PhD mathematician, if I have to stand here for a couple minutes, 5 minutes, and just kind of sort through a bunch of algebra in my head and figure out, the better way to go on this, then if you're sitting there for 5 minutes, when you're doing this on paper, trying to figure it out, or if you're sitting there for 20 minutes, like that's normal, that's good, that's where you should be. So good. Um, let's see. I think the thing that we're lucky with here, that all of this is being added and subtracted. So now that I have e raised to the power, I can break this into separate pieces. So we can have the absolute value of y equals e to the -1 over x. And then really this would be divided by, so this is going to be multiplied. So it's going to be times e to the c, and it's going to be divided by, interesting. That's kind of fun. In fact, could I take that up as a power? I could if I wanted to. Let's see if that's useful. But then on the bottom, we're going to have e to the natural log of x. Again, that negative is telling me it's on the bottom of the fraction, so I don't, that flips it to the bottom of the fraction is the way I think about it. So you don't need the negative anymore. Now, e to the natural log of x is just x, because the e and the natural log cancel each other out. So we've got a good bit more simplifying that we can do here, which is really nice. So e to the -1 over x times e to the c all over x. That's going to help us, because then when we plug in stuff, we don't have to deal with a bunch of domain issues, things that can't be calculated. Interesting. Means like let me plug this in my mind and see if this calculus any issues otherwise. I think this is where, and again, I won't go into much of the theory of it, but we can essentially take these absolute values off. Because the absolute values still really tell me this is plus or minus, so I can basically tailor plus or minus once I plug in the -1, be whichever one I need. Because of that, it's just now this is just I can take that off. That's just y equals. That's probably. I think the only thing I would do here is I'd probably recombine these together, because it'll be easier to try to add these together, basically, rather than. Yeah. No. So I'll recombine those. So it'll be e to the c -1 over x over x. And now what I can do is I can plug in -1 for x, plug in -1 for y, and go solve for c. So this is my general solution. So this is my general solution. Now what I'm going to do is I'm going to plug in my initial conditions. Plug in initial conditions. So everywhere I see next, I'm gonna plug that in. So what I end up with is -1 equals, it's gonna be e to the c minus 1/-1 is a -1, so that's really c plus 1 over -1. And then multiply by -1, so we end up with 1 equals e to the c plus 1. And we know that when you take a base, you raise it to a power, you get 1. What does that power have to be? It has to be 0. So 0 equals c plus 1. So what is c? C is -1. So c is -1. Which means I can then go back to my, sorry, it's starting to get crowded. I can then go back to my general solution, plug in -1 for c, and then I have the y equals, I have this specific solution, or they call it particular solution or specific solution. So -1 minus 1/x, e to the negative all over x. This is, well, no, sorry, in this chapter, we'll say particular solution for the next chapter, because it does mean something, it still means something general and broad. But I'll call it just the exact solution. So it's the exact solution as a differential equation for those initial conditions. And that's not only what you're doing in this section, but that's essentially what we're gonna be doing. You'll see basically for this whole course is we're gonna go through looking at a bunch of different types of differential equations and basically developing solution methods for them, by figuring out solution methods. And that'll give us general solutions. Then we'll go back once or twice and we'll look at those differential equations or a differential equation with an initial condition. So basically we just end up doing the same solving and attacking this little extra process on the end of plugging in your initial conditions to find out what your concentrate. And that's it. So this was separable equations, that was 2.2. The next video will come back and look at, I think it's exact equations. All right, I'll see you guys back for the next video.